Hello everyone, welcome to this new video about software exploitation. In this video we will be discussing how to exploit another case study related to uh, structured exception handler, which is SEH. We'll be using the vulnerable server from Stephen. So Stephen Bradshaw, we're using his application. We'll use this one first, and then we'll do another case study on another application. Okay, so this video again is about software uh, exploitation, and it's going to be covering how to exploit the vulnerable server but using SEH. Okay, so let's get started so we can get this done. And if we do vulnerable server, we'll get this telling us that we need to open the firewall so our clients can connect to the server, okay, from another location. And let's just check the ports, etc. So if we do netstat minus protocol TCP minus a, then we should be able to see that, yep, this is the one. So this is where vulnerable server is running on port 1234. Okay, so vulnerable server is running here on port 1234. It's waiting for connections. Let's go to our threat actor before we start using the code, just to confirm that this is actually the case. 192.168.8.10, and then we are going to be connecting to let's put this aside for now, port 1234. So welcome to vulnerable server. You can do help, so I'll give you help then. So everything is good. We are going to exploit the vulnerability in the Gmon. I'm not going to go over how to find that vulnerability, at least in this video. So the fuzzing part, or how to discover the issue with the Gmon command, is out of scope of this video. Okay, so let's get started. And as you saw here, I have a template which I will be starting with. Okay, so we are importing the socket, the IP address, the port we want to connect to, and I'm going to send 4,000 bytes in order to exploit this application. Okay, uh, this is our try except code. So connecting to the host and the port, receiving as you saw the message from the client, we will be receiving it from the server, sorry. And then we are just going to print whatever data we received. Then the vulnerabilities in gmon space slash and then some buffer and then /r/n, and then this is just printing something happen in case this doesn't work, closing the socket, and then finally, just to make sure we have sent successfully 4,000 bytes. So let's just bring this a little bit like this. Okay, and now let's do Python exploit one. So if we let's attach this to the debugger also, so we can get our debugger. And let's attach our vulnerable server. Okay, should be paused. Okay, so if we click run, it's now running. Okay, so all seems good. Let's go on our code. So we successfully sent a buffer of 4,000 bytes. Okay, and we can see now that the application paused. If we look at the stack and at the registers, so at the stack we can see our Gmon here, and then we can see the A's that we sent. Like if we go down all the way down here, we can see the A's. And also, since I went down, you can also see the pointers to the next SEH, and the SEH handlers have been overwritten. So if we go to view, go to SEH chain, we can see that they have been corrupted. Okay, so we can see that they have been corrupted. We can also see that in the registers there are some of them are pointing to these values. Okay, So now what we need to do is let's say we managed to create an exception. So the program, let's say, because it's in the debugger, the debugger captured that. Okay, but now let's say we tell the program to try and use the handler to handle that exception. So I'm going to do shift F9 once, and let's see what's going to happen. Uh, so great, we can see that our A's got now into EIP. So what does that mean? It means we did not have direct control to EIP. We needed an exception in order to control EIP. Again, we did not, like the similar, the previous case studies, especially the vanilla buffer overflow, we don't have, similar to those, that our data is going to be pushed into EIP or copied to EIP, or EIP is going to load them directly. What we did now is we triggered an exception, and that exception, once let's say the system or the application tried to execute it, we managed to push or copy load the A's into EIP. Okay, so we do excuse me. So we do have control over EIP, but that's after we trigger an exception. Okay. So now we know that we have control. Let's restart, and now the next step is to know the offset to our control, because again we send 4,000 bytes. Which 4 bytes out of those 4,000 bytes that we sent are the ones that will end up in EIP? We want to know that. So if we go back, and before I usually do, so if I do cp exploit and do exploit again, 2, now let's me load 2. So I'm gonna get this over here. Yeah, so let's load number 2. Okay, and now let's do MSF pattern create minus length 4,000, right? We want a pattern of those 4,000 bytes. Now don't double click, by the way, on this. I do recall I did this by mistake once when I was testing things. Go and copy and paste them. So if we copy this, okay, and now in exploit 2, we are going to change this with these values. So now let's run the code again. So Python exploit 2, and we should have also sent 4,000 bytes. Great. So if we come here, we can see again same thing. ECX got overwritten with some data. EBP, same thing. Over here we can see Gmon, and if we like go down, we can see all of that. These are part of the pattern that we are sending now. Also, if we look at the SEH, so if we go here, the SEH chain, we can see it has been corrupted with these values. So let's now go back just to see what's going to happen, because now this address is going to be loaded. So if we do shift F9, okay, so if we do shift F9, and as you see, the address of the handler got loaded into EIP. Why? Because we triggered an exception. The exception is now calling the handler, so it's calling it by going to this address, okay? And now, since this address is actually, there is no handler there, we have control over EIP, and there is nothing really there to continue. So it paused. So now what we need to do is we need to copy this. Okay, so let's create some notepad. Yeah, let's just open this. And I can't copy it across my systems because I'm running these all remotely. So what I will do is I will save it on a piece of paper here, and then just copy it. Type it over. Where is my some notes? Yeah. So if I do some notes here, let me type them. So this one we restarted it, right? So okay. Now let me just save this. So it's 6D, right? Where is it? 6D 4 5 3 3 6D. Okay, so everything is running, all good. Let's go back, modify our code. So let's me copy cp exploit 2 out exploit 3.py. I'm gonna do exploit 3. So let's close this one. We don't no longer need it, and we don't need number 2 anymore also. So what do we need to do now is let's find the offset. So msf pattern offset, and we want to query the value that we got, which is 6D 4 5 3 3 6D. Okay, so we can see that the exact offset is at 3490. Okay, so the exact match is at 3490. Okay, so let's take that and let's go here. So just gonna save this over here so we can remember. So now what we need to do is we are gonna do some modifications. So I'm gonna do a pad, and then here I'm gonna do A, and so 3490 was the address for the handler. And if you remember correctly from our previous videos, our handlers or our exception, so if let me do the paint, yeah. So if you remember from previous videos that each SEH record has something like this. So we have here next SEH record, and we have over here SEH handler. Okay, so this one, if I do, let's say if I do just this for speed things up, so if I do that, or like here, okay, I know I'm not the best when it comes to design, but we should be fine with these. Okay, and then let's say this one. So this one, the last one, let's say it's pointing, if you remember, to FFFF. So it's going to be 0x1 2 3 4 5 6 7 8. Okay, so it's going to be like this, pointing there, while this one is going to be pointing to wait a minute. Told you I'm not good at this. So how are we going to do this? So let me just do it this way. I'm not a good designer. And then like this. And okay. And then this one is pointing here. So let's do this. Let's do that. So actually, let me do it this way. Just again. And then we have, okay, we have this. Come on. Okay, and then you have this. So this, then this. Okay. And then this is pointing to the next one. So this one, let's do it like this. Just gonna choose another color so we can see. Okay, like this, and then like this, and then here, and then yeah, finally we reached our final destination. Okay, So think of it like this. This one is pointing to the next, and the next one is pointing to the next, and the next one is pointing to this one. So when we triggered the exception, what happened is these 4 bytes are the ones, or let's say this one, were the 4 bytes that got pushed into or got loaded by EIP. Okay, were the ones that got loaded. So when we calculated the offset, our offset was actually to this end entry, not to this one. So what that means is we need to take 4 bytes off. So if we want to overwrite, let's say, the next SEH with, let's say, with B's and the SEH handler with C's, then the offset that we found again was to arrive at this area, not this area. So we need to take those 4 bytes off. Let's see that in action, actually. So let's see that in action. So we have here this amount of value. So pad A, and we need to multiply that by 3, 4, 3, 4, and not 90, but 86, right? And then let's say next SEH, that's going to be B's, okay, 4. And then the SEH handler, it's gonna, let's do C's. So, and now what we will do, we need the rest of the 4,000. So let's do some more padding. So we can do, by the way, pad 1, now say pad 2, and pad 2, yeah, pad 2 equals, so we have 4,000, right, minus length of pad 1 plus NSEH plus SEH, and so all of those, and then that's like this, and then this multiplied by, let's say, these. So that's where we can see that, yep, I think we should be fine. Okay, is our application running? It is. So let's get started. So now if we run the code, which is the exploit 3, Python exploit 3, we should run buff is no, okay, let's do this. So buff equals, I think, pad 1 plus next SEH plus SEH plus pad 2. That's how our buffer looks like. So let's run the code again. Okay, so we sent successfully 4,000 bytes. Let's come back here. Again, we can see we have the exception. So the application was captured by the debugger. If we go down here, we can see the A's. Let's go a little bit more down to see where are our B and C's, etc. So just to have a look at them, so we can see B's, the C's are over here. If we also go to the SEH chain, we can see that the SEH handler got overwritten with the C's, right? And the next SEH record is at 42, 42, which are the B's. So if we now hit Shift F9 once, we will load the C's into EIP. So EIP is gonna be calling the C's. Why? Because this is where the handler is supposed to be located. Now, look here at a couple of things. First, EAX has been zeroed out. EBX has also been zeroed out. And you can see also ESI and EDI all have been zeroed out. So there is nothing pointing to our data. But let's look at the stack. So if you look at the stack, the first address pointing to some area in nt.dll. The second address is pointing to some other location. But look at this address. It's pointing to where our B's are. So if we just follow and dump, by the way, we can see that this address right here, it's pointing to our, it's pointing to what? To our B's. So we are now pointing to this area. So at the beginning, we triggered an exception. The system tried to load the handler. The handler was unsuccessful. So now what we can take advantage of is the next SEH record, because that's how the chain will work, right? It will first come here. If it can solve the problem, then that's good. If not, then next SEH will come here. Can this handler solve the problem? If yes, good. If not, then go to the next one until we reach the end. So now we can take advantage of this by doing uh, by let's say having our shellcode point there. So if I, instead of having next SEH pointing to the next handler, if we point it to our shellcode, then we will be able to execute our shellcode. But we need to do one thing. So this is located two two addresses down in the stack. So what that means is I need to get rid of this one, I need to get rid of this one, and I need to get this one loaded into EIP. So you can do multiple ways. Let's do in this example the basic way, which is what people mostly know about, which is pop return. So what you can do, by the way, if you go to the the executables, and let's say you go to this, just one way of doing it, and if you right click and then do search and then go to sequence of commands. So what you can do here, you can say I want to search for pop register 32-bit register, pop a 32-bit register, and then I need a return instruction. So if we do this, we can see that we have this sequence of instructions, which is the pop some register, pop some register, and these are all 32-bit registers, and then we have the return instruction. Now I know there is a zero, a null byte over here, so this is not going to be used, but I just wanted to show how you can do this manually. But why do manually when we have Mona available? So we can do Mona, and there is an instruction here or a command called SEH. So we can do Mona SEH, and it will go find all the pointers or all the addresses that I could use in my exploitation. Okay, so let's get that and see what we need to do next. So Mona should be here. Okay, let's see which address we are going to use. So we can see these are all the addresses. So this is where the ESS function is loaded at 44. This is the base 44, 55, 000, etc. We can see the addresses that we have. We can pick any one of these, by the way. So we can see this, not all of them, sorry, but we can pick some of them. So we can see this one works. This one will not work because it starts with a null value, right? And this one is from the ESS function.dll. So we can definitely take this one. Let's copy it. Okay. And one other thing that I probably need to mention here before we start working on this, let me go back, by the way, let me go back. So in order to exploit this application, we need to find a module, okay, or an image. So ESSDLL, this image, or the vulnerable server is also an image, okay. We need that to be, or a module, whatever, depending on where you read it. It's sometimes you read it a module, sometimes you read it an image. So we need these to be, we need the module or the image or whatever you want, the executable. We need that to have no safe SEH. Excuse me. So we need to find the executable that is not compiled with safe SEH, okay? Because if it is, then we will not be able to use this method. Why? Because safe SEH, what it will do, it will pre-register the exception handlers once the system loads them, and you can like imagine they get stored in a table, and then when an exception happens, the system will check the address on the stack with the address in the table. If they match, then all good. If they don't match, then we probably have a problem, and some of our addresses have been overwritten, so the system will not continue. So in our case, ESS is not compiled with safe SEH, and I know that because I did the compilation in this case. And we can also see the vulnerable server is also not compiled with safe SEH. So all good here. This address should be fine. Okay, so we have, I'm just going to write this down. So we have 4455 1A34. Okay, so let's now go back here and use that. One other thing which we will, I'm gonna try to break down this problem, by the way, one at a time, but you'll see that we still have other problems that we need to achieve. So let's overcome the first one, make sure we can load this address into EIP, and then we'll figure out what other problems we need to bypass. So if we do this and start the application, and let's put a breakpoint on our pop-up return. So if we do this, okay, so we put a breakpoint here. We can now go back. This could be now number 4. Let's name it number 4. Okay, so now we are going to replace the SEH, right? We're going to replace this with the address we found, which is 0x34 0/x, I mean 1A/x 55/x44. So which is just for the record, pop return. Okay, so this is the address of pop return. All good. So we should be able to now run number 4. So all good. We sent the 4,000 bytes again, and we can see the application stopped, triggered the exception. We can see in the SEH chain what is happening. Okay, so we can see that now our handler is pointing to 44551A34, and the next one is at 42 42 42 42, which are the B's. So if we look down here on our stack, we can see that everything has been, see, so this is the pointer to the next SEH, which is the B's, and this is where the handler is. Okay, and then we have the rest of the data. Okay, so now what we do, if we do Shift F9, so Shift F9 will load the address of the pop return. So now if we look, by the way, at this address, because it's, again, we said it's 2 bytes, sorry, 2 addresses below. So if we look at this one and follow and dump, we can see this is where our B's, and then our the pop return, the address for our pop return. So we should expect, once we run all of this, to get this address loaded into EIP. So let's do that step by step. So if you hit F7, we are going to remove the first address, 9F82. We are going to put this value into ESI. So we did that, ESI now. Now ED60 is going to be loaded into EDI. So look at this, going to be changing ED60. And now this address, we are going to do the return. So it's going to be loaded into EIP, and the EIP will try to execute that. So if we do that, where did we land? We landed at our B's. So now we are at here. Why? Because now we are trying to call the next SEH record. Okay, go to the next one, because this one did not solve the problem. So we need to go to the next entry in order to solve that problem. Okay, so now we have something over here which we need to come up with. So we need to bypass this and make, let's say, we have these 4 bytes, and we need to, let's say, jump into this area. Okay, jump into this area. But we still have another problem here, by the way. So if we jump into this area here, which is the D's, right? This is the D's, okay, the 44. The problem here is, if we look at this, let's go down a little bit. There's not much of space in here, by the way. There's not really a lot of space in here. So based on even our code that we've done so far, we didn't see any shellcode that we can run within, how many bytes are this? So we have 16, 16, 32, we have here 4, and then we have here, so we have 36, then 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 45 bytes, which is not enough, by the way, to run our shellcode. But what we will be doing is something else. So first thing, let's overcome this problem. So we are at this location. We need to jump over these addresses. We need to jump over these values. We want to jump over them, right? And step into this area over here. Okay, so we want to jump over this and step into the area over there. Okay, so let's get started. So this is where we landed, 42, 42, and we want to, again, we want to jump this area so we can land in this area over here. Okay, so let's see how we are going to do that. So this is, let's restart, and let's go here, start the application, all good, put a breakpoint. We want to make sure we can follow one by one. And now let's modify our code again. So this will be 5. And now what we will do is, instead of the bees, we want to do a short jump. So what the short jump is 0x EB, and then 0x. Let's do, so we could do 0, 6, just 6 bytes. Okay, we can jump over 6 bytes. But you might be asking me, why am I jumping over 6 bytes while I only have 4 bytes ahead of me that I need to jump over? The answer is, our addresses are all 4 bytes, right? So what that means is we need to pad these. So I'm going to pad them with knobs. So this means the jump will jump these 6 bytes and then land in this area over here. Okay, let's see it in action. It's always good to see in action. So 5, run, 4000, all good. We can see the crash. We can go to SEH, also the handler chain, I mean. Look at that. We have the entry to our pop, and then we have the next SEH is located at this area. Okay, good. So now if we, again, shift F9 once, we are loading the address of our pop-up return. Okay, great. We need to go to this address over here, which is where our, so if we follow dump, this is where our jump instruction is located. So we need to pop, and then return into this address. So F7 again, and then the return 3F B3FFCC is going to be loaded into EIP. So EIP is now loaded at this area. So if you look at here, what is it saying? It's a short jump, like I said, and this short jump is going to be jumping into the address B3FFD4. So B3FFD3 is this one. So B3FFD4, this is where this instruction is going to be jumping into. So if you want to put a breakpoint like here, and then, for example, hit F9 if you want, you will see you get stopped by that. We don't really need the breakpoint. I just put it to run the F9, to run the application. So we now landed into this area, and we have all of this area here to use for our shellcode, but unfortunately, it's not enough for our shellcode. Now, this is the reason why we use a debugger, right? Because we can now look into the head or into the memory of the application. So by using the debugger, we are capable of looking at what's currently loaded into, let's say, the memory address space of this application. So we can see here are the Ds, but let's go a little bit up. What do we see over here? These are all what? These are the A's of our the A's of our buffer that we send. So you see, these are all A's. Go down a little bit. This is not the A's. Yep, here they are. So we can see these A's. These are all our A's. Okay, these are all our A's which are available over here. Okay. So what do we need to do? So it means this time our buffer is in not after ESP, or like if you remember in the previous cases, it's not after our jump, it's in the previous memory location. So what does that mean? Let's see here. So we need to figure out a way to jump backwards. So we need to jump in a negative, like in a way backwards, in an address backwards. So we need to find a way to do that. Okay, so we need to find a way how we are gonna be doing that. So this is where this code comes into play. So let me load the code. I have it over here and jump back. So this jump back instructions, a set of instructions. First, you can see this is poppy CX, then decrement CH, decrement CH. Each decrement, by the way, each one of these decrements actually is decrementing the higher half of CH. So that means it's decrementing the register with 255 bytes. Okay, and then it's doing the jump PCX. But by the way, this shellcode, if we call it a shellcode, by the way, this one starts the execution from here. That's the important thing to keep in mind, by the way. This one starts the execution exactly from this location. Okay, this one again starts our execution exactly from this location. What is it going to do? So in memory, what this is going to do is, if I go back here, the application does not know where in the memory or which address is currently loaded in, right? So we need a way to figure out where am I in memory, and then so we find that address, and then from that address I calculate negative addresses backwards. So I calculate backwards in order to reach addresses in this area. Right? Again, we need to find where we are currently loaded in memory. So we need to find this address over here. Let's say we need to know that we are operating in this area. How can we do that? This is what's going to happen. So what this is going to do is going to call a relative jump. Okay, but because we are going to be doing a call, right? Because we are going to be doing a call, what this will do, because a call instruction, what happens, if you remember, it will push the next instruction where onto the stack. So once this call is going to be executed, the next instruction, which is, let's say, the EIP, is going to be pushed where onto the stack. And then the first, and then it's going to call here. So this one is going to call over here. We are going to debug this, don't worry. And then poppy CX, so the first instruction which we pushed onto the stack was the address of the next instruction, right? So now we know where are we located in memory. We start decrementing, and then we jump to that address that we decremented. Let's see it in action, better than just talk about it. So if we go to F5, let's do this as F7. And so this one is this. And now what we are going to do, we're going to do some modifications. So we're going to do, I'm going to add some pops. Sorry, not pops. Not knobs, I mean. Knobs 1. I'm going to do X90. And then I'm going to do jump back. And then just add this value over here. So what do we have left? All good. We need to update this. So we have pad 1, next SEH, and then we have knobs, right? Knobs 1, then we have the jump back instruction. Okay, so jump back instruction, all good, all good. So now let's run the code again, F6, but I think we need to, we need to restart. Good. So restart again. Yeah, exploitation takes a lot of time and trial and error. What did I do? And let's run, get our breakpoint. 2. You come over here, and now let's run this code. Oh, we sent something wrong. Oh, we didn't send 4 of them. Okay, sorry about that. I'm gonna have to repeat this. I don't really need to repeat it, but just so we know what we are doing, and just to make things easier for you. We really don't need to repeat it, by the way, because at the end we will land in that knob area, one single byte of knobs. But anyway, let's do it again. I hope this time we have everything figured out. Why did that happen? So what did I miss? Pad 1, SEH, SEH, knobs 1, jump back. Oh, we didn't add them to the buffer. Wow, keep forgetting these small pieces, by the way. So knobs 1, and then we have the jump back. Okay, we forgot to add them to the buffer, which is being set. We did the calculations correct, by the way, but we didn't add them over here. So let's restart again. It's good that you see even my mistakes. So when you get into these mistakes, don't get frustrated. That's totally normal and totally fine. Okay, so let's do this. Okay, so now let's run our code. Okay, here. Okay, now 4,000 exactly, and we have everything all good. We can see here, we can also see our SEH got overwritten, and this one is pointing to some corrupted area. Okay, good. Let's go back to the CPU and let's do Shift F9 once. And now we are at the pop return, right? Yep, now we are at pop return. So pop, and then the return should take me here, which is where my jump is located. So if I do F7, great. So now we are at the jump, short jump instruction. Where is this going to take me? This is going to take me, by the way, to jump into this area. Now, if we do that, by the way, this is some mistake that I've seen people do, and they like the shellcode will not run correctly. Because what's going to happen here, if we do now F7, so if we do F7, we are going to jump into this address over here. So if I do F7, we are there, right? Okay. But now what's going to happen is we are going to execute these sequentially. So the execution really did not start from here, and we did not find where we are currently in memory. We are going to depend on this value here and pop it into ECX and then just decrement that. So this is wrong. What we need to do is we need to jump from this location directly to this location. Okay, so the jump, we need to modify our jump again to jump from this location directly where to this location. Now, how many bytes do we have in this path? How many bytes do we have in this path? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we need to jump 19 bytes in order to do what? Arrive at this area. Okay, we need to jump 19 bytes. Let's restart this and do the calculations again, just to make sure. Again, the reason why we want to jump that is we need that part to be executed first. That's the first part that should be executed. So what we need to do here, instead of jump 6, it's going to be, so these are 6, right? And then we have 4, then that means 10, 11, 12, 13, 14, 15, 16, 17, 17, 18, let's see, 18, 19, and this brings me at this location, which is the jump backwards, right? E8 is where, yep. So 19, we need to jump 19, right? We need to jump 19, and let's just find what is 19 in hex. Okay, so if you have 19 and convert it to hex, okay, and it should be 1 3. So we are going to jump 1 3, and yep, let's do that. Let's now run the code again. Did I restart everything? Yeah, okay. So let's do this again. Can bring that back here, we don't need it anymore. So we sent, all good. We have the crash. You can check ECH, our SEH chain. So all good. Let's go back and do Shift F9 once. And we are at the the pop instruction. So F7, F7, then return. We are at this. We are at this address. Let me just. And now if we look at this address, so you can see the jump short is gonna jump to 00C8FFE1. So if you look down here, 00C8FFE1 is where this address over here is. So we are gonna jump immediately to our call instruction, and that's how that's what we want actually, because again, the idea, the whole trick in this shellcode is we execute it backwards. So we start the execution from here, not from here. Okay, so let's see why we are going to start it from here. But let's hit F7. So F7, now we are at this location. So now look at what's going to happen. Look at what's going to happen. So see this address here, C8FFE6. So let's just remember at least FFE6. This is going to, when we do the call, this is going to be pushed where onto the stack. So look at what's going to happen. So F7, see, FFE6, okay, what happened to it? It got pushed where onto the stack, because we did a call instruction, and the call, what it will do, it will save the next instruction on top of the stack and then go to that area. Okay, go to that address. So now we are going to do what? We are going to do a pop ECX. So this value now is going to be popped where? Into ECX. It's going to be stored there. So if we do F7, look at that. We have FFE6, that address is now stored where? In ECX. This is how the trick all plays in, that we managed to find where, or let's say the application, we are telling the application where are you currently, where is, what, let's say we are giving the application some address in memory so we can know where it's located in memory, or we now know where are we navigating in memory, because we now know we are in this area, right? Because we loaded this address where into ECX, right? So now the application knows, or we know, that we are in this area. So we managed to find that. Now we want to go backwards. So that's why we are going to be decrementing CH. So if we decrement that, so if we decrement, so now look, where is CH pointing, by the way? CH is, ECX, sorry. ECX is pointing to the A's. So if we go to that address, by the way, if we go, let's copy this just to show you what's going to happen. Where is this address? If we go to this address, you can see it's the A's, our A's that we found. Okay, let's continue the execution. If we do F7 again, so if I go F7 again, I'm going to do another decrement. Again, see, it's still pointing to the A's. So if I copy this and go here, I'm in the A's, by the way, but I'm in a 255 bytes address further upwards. Again, let's continue the execution. So F7 again. Now we are at this location. So we moved up even more, 250 bytes backwards. So if we go to this address here, just to see where are we? So we are now in this area, in this area. Okay, see, the A's are still there because if you remember, we had, how many A's? We had 3,000 something, and we only moved backwards, by the way, by 762, which are 3 times 254. Okay, now if we look down here, we have all this space, by the way, to put our shellcode. So if we continue going down, yeah, see, this is where we are. We have all the space to put our shellcode. So we have 762 bytes to be used for our shellcode. Now, if we continue the execution, we are over here, jump PCX. So this is where ECX is loaded. We are now going to do the jump. So if we do the jump, we are at this area. And if we had our shellcode, we could have executed our shellcode off of this address over here. Great. I hope you understood what happened in here. Okay. If you didn't, please go just like go back a little bit in the video recording and watch the step-by-step debugging of this, so you'll be able to understand what's going on. So let's restart this and do some calculations. By the way, now we need to do some calculations, and it's a trial and error. So let's put a breakpoint at our, which was, yeah, this one, the pop-up return. So we are good here. Let's modify this code and name it number 7. Okay, so what do we need to do now? So we need to add our shellcode in this area, right? This is where our, let's put just shellcode. We need to put our shellcode in this area. That's what we need to do. So we are going to be jumping backwards. So let's see if we can get a calculator. So calc, yep, let's get this. So we are going to be jumping backwards or moving backwards 762. So we have currently 3486 minus 762. Okay, minus 762. So 2724. So 2724, if we do, let's say, if we do 27, so if we jump backwards, let's modify this to be, this is no longer going to be used. Let's modify this to be 27, yeah, let's do this 2700. Okay, let's do that 2700. I'm going to put some knobs. So our shellcode will land in there. Okay, how much knobs do we need to put? Let's say we put so if we do 2724 and if we put like 50 knobs here, how much do we have over here left? So plus 50, and it's this. Let's see how big is our shellcode even, by the way. We forgot to do that. So let's create our shellcode. I'm going to use this, and I'm not going to be explaining in this video how I found the bad characters. We'll do that in another video, but I'm going to, the null byte, the space, the /r/t, which are the new line feed and the carriage return. I'm going to exclude those, and I'm going to generate this shellcode. So let's do this. Okay, and I'm going to copy all of it. And it's 368 bytes. 368 bytes. Let's see what's going to happen here. So if we do our shellcode, write it over here. Save that. Let me bring it just a little bit here so you can see what's going on. So we don't need this. I'm going to remove that. Okay, so I have our shellcode here. Let's do this. Let's do that. So we have 368. And where is our calculator? So if we do this plus 368, how much do we have? 3124. Is that still enough? Yeah, 3124. Yep, that should be enough. So we can do this. We can have the pad A's, and then some 50 knobs, right? And then our shellcode, which is, we said the size is 368, by the way. again, this is trial and error. You might hit it, you might need to just come back and modify your calculations. And then now what we have left from our 3490, so if we subtract this value from this, we should add 348 of knobs again, maybe. So we can do knobs. So I'm going to rename the knobs, by the way. So this is knobs 1, knobs 2, and I will update everything. Knobs 3. Okay. So this is equal slash x 90, and then multiplied by this value. So hopefully this will give me, let's calculate them, by the way. So let's calculate everything. We have 2700 plus 50 plus 348 plus the shell code, which 368, right? And then we have the next SEH, which is 4 bytes. We have the SEH, which is also 4 bytes. And then we have the NOPS 3, which is also 4 bytes. And then we have, how much is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 over here. 3492, and I'm assuming this one is going to do the calculations for everything else. So we need to update this. So we have pad 1, then we have NOPS 1 plus shellcode, right? And then we have the NOPS 2, then we have next SEH, we have SEH, NOPS 3, right? And then the jump backward. So we can just copy this, by the way, and just put them over here. Put some spaces so it's easier to read, and we should be good to go. Yeah, we are nearly there. Okay, so again, what we did, guys, is pad 2700 of A's, then we have 50 knobs, so hopefully our jump backwards will land in this area, because if we do the calculations again, by the way, we do the calculations again, like if we do 368 plus 348, right, we are 716, and we are actually going to be jumping backwards 762, so it will land in these no operation area. And then we have, just to fill in the rest of the buffer, because this should be this until our next SEH should be 3486. So this is now 3486. Next SEH, etc. All should be good. Let's now do the run. Before we do that, let's make sure our handler is working as well. So let's do show options, make sure everything is correct, and everything should be good to go. So run. Okay, and now let's run. This is number 7. So we 3492 bytes, we have a problem. What did we miscalculate? What did we miscalculate? So pad NOPS 1 shellcode NOPS 2 next SEH NOPS 3. Oh, we forgot the second pad, which is pad 2. I deleted it by mistake. Pad 2. Okay. Excuse me, let's restart again. So all good. Let's go here. at the breakpoint, and now again it's good you see my mistakes, so that way, yep, 4,000, you know that these stuff happen and not everything will go exactly the way you want. So let's see here if we can see the values are on the stack. If we go down to the end where our values have been overwritten, so we can see this is where our the knobs, then our shellcode here, and then we should see some knobs again. Yep, so we can see some knobs, and then we can see over here the address to the next SEH, the SEH handler, and oh, so yeah, this is where it should be the last one, but all of this is overwritten. So this is where our next SEH handler, and this is where our current handler. So if we look here, you can see them again, SEH chain. You can see this got overwritten with this value, and this got overwritten with this value. There's something weird going on here. I'm not sure. Let's see, because we might have done a mistake. So if we do Shift F9, okay, I think we did a mistake somewhere. We miscalculated something and we got stuff shifted. Let's do this. Okay, so it's most probably, by the way, we miscalculated here at the beginning. So let's get our calculator here back again. So we have 2700 plus 50. Okay, then we have 368. So we have this value, right? And then if we add 348, we have 3466. Wait, let me just do this again one more final time. So 2700, right, plus 50 plus the value of the size of the shellcode, which is 368, and then the rest of 348. Let me just copy this so I can use it again. Oh, through 3466. So we are off by 3466. We are off by the way, by 20 bytes. So what I'm going to do is I'm going to put, let's say, 60 here, and let's do, yeah, I'm going to do 70 actually here even. Let's do 70 here. So I'll guarantee that we are going to land in the knobs area. So now if we do this 3486, exactly 3486. So now we should be good. Now we should be good. See, I told you it's a trial and error. And here all good. Let's now run the code again. Okay. So 4,000 all good. We can see, let's make sure our handler is running. Yep. So now if we look, let's check the SEH before we continue, by the way, because it should be, yep, now we are all good. Now we are all set. We miscalculated things. So now if we do Shift F9, we are going to load the handler address, so which is the pop return. So pop return to our jump. The jump will go where the jump is going to do. I'm going to debug this also again, so you can understand it. It's going to go to A6FFE1, which is here, A6FFE1. So we'll jump to this location, and I will, by the way, in other videos I will do modifications to this, because sometimes maybe you want to jump backwards more than 762 or maybe less than that. We can still do that, by the way, but we'll need to modify this shellcode. It's not complicated. You'll see how I will do that. It's not complicated. So now if we do F7, we are at the call. So the call, what it will do is going to save A6 FFE6 onto the stack. So if I hit F7, so we see A6 FFE6, that address is now stored where? Onto the stack. Okay, now we are going to do a pop ECX. So this address is going to go into ECX. So we are kind of we are actually, what we are doing here again is we are trying to find where are we located in memory, because we need to know where are we in memory in order to be able to move around in memory. So now if we do pop ECX, it's going to be popped into ECX, and you can see it's pointing to this address currently. So it's currently still pointing to FFE6, which is here, FFE6, which is the Ds. This is where our Ds, if I go follow and dump, okay, this is where our Ds are. So now look what's going to happen. So if we do F7, we decremented that value, okay? If we do F7 again, so by the way, if you want to do, let me show you. So if we copy this and go to the address, let's go there, see what's there. So we have the knobs, okay? And now if I do F7 again, so we did another decrement. Let's see this address. Where is it? What's over there? So if we go here, so we are here probably in the middle of our shellcode, by the way. We are probably in the middle of our shellcode, so we still need to jump backwards more, 54 bytes more backwards. So if we do the next instruction, which is decrement SEH, now we decremented even more. So if we go here, see where are we located. So we are going to be landing in this area, by the way. Okay, we are going to be landing in this area. So let's now do jump ECX. So it's going to do jump to this address. So F7. Okay, let me actually put a breakpoint here just so you can see it's really going to jump there. I'm going to do this. It's going to tell me, okay, no problem. And now if I do the jump, it's jumping to the address exactly where we have our breakpoint. So now if we do, if I do this, I want to, yeah. Now if I do the execution, you can see that we are going to be executing all of this knobs. And then you see our calculation was correct. We are going to land before our shellcode and be able to execute our shellcode. So if you hit F9 now, you should be able to see a meterpreter shell open on your system, on your threat actor system. Still running, and here we go, we have access to the system. So we managed to exploit it using SEH, using this long backward jump. I hope this was clear to you how it was used, how do we use it, and I will do a different video on how we can modify this, because again, we can play around with this and modify it and understand how it really works, in case you need more than 762 bytes, or in case you need maybe less than that. Okay, so we can do this in another video, but for now I hope you understood how this works, and you learned something out of this video. If you have any comments or any notes, please let me know. But that's it for this video, and I will see you in future videos. Thank you, and bye-bye.